Hey there, and welcome. Today we're going to do something really cool, a virtual teardown. We're taking one of the most fundamental pieces of electrical engineering, the DC machine, and we are stripping it down piece by piece to see what really makes it tick. All right, let's get our hands dirty.
Have you ever really thought about it? What's the secret sauce inside an electric drill, or your kid's toy car, or even an e-bike? Well, chances are the answer is a DC machine. It's a piece of tech that's so common, we kind of take it for granted. But it's the powerhouse behind so many things we use every single day. So let's pop the hood and see what's going on inside.
So what is a DC machine, really? At its heart, it's an energy converter. And it's a two-way street, which is what makes it so incredible. You put electricity in, you get motion out. Boom, you've got a motor, but you can also spin it with some other force, and you get electricity out. Now you've got a generator. It's this beautiful, elegant duality that makes it just so versatile. Now you might think something this useful has to be super complicated, but here's the amazing part. It's brilliantly simple. Everything, and I mean everything, that happens in this machine comes down to the interaction between just two main parts, a stationary part, which we call the stator, and a rotating part, called the rotor. That's it. Let's break them down.
Okay, so let's start from the outside and work our way in. First up is the stator. This is the machine's anchor. A good way to think of it is like a house. It not only protects everything tucked away inside, but it also plays an absolutely critical role in creating the magnetic environment where all the magic is going to happen.
So this house, the stator, is made up of a few key components. You've got the yoke, which is the outer shell, the main poles, the field windings that are wrapped around them, and often you'll find these smaller helper poles called interpoles. They're kind of squeezed in between the main ones to make sure the machine runs super smooth and efficiently. Every single part has a job to do.
The yoke is really the backbone of the whole thing. It's this rugged outer frame, usually made of steel, that gives the machine its strength and structure. But it does more than just hold everything together. It's also a highway for the magnetic field, making sure that magnetic flux has a nice, complete path to travel all the way around the machine.
Bolted to the inside of that yoke are the poles. Now, here's where things get really clever. You see, the poles aren't solid chunks of steel. They're actually made of really thin, stacked layers of steel called laminations. It's a smart design that helps cut down on energy loss from these pesky, wasteful little currents called eddy currents. And those flared ends? We call them pole shoes, and their job is to spread that magnetic field out nice and evenly. So, how do those poles get their magnetic power? From these guys, the field windings. They're just insulated copper wires coiled tightly around the poles. When we send a direct current flowing through these coils, they basically come alive. They turn into powerful electromagnets, and they generate the strong, steady magnetic field that this whole machine is built around.
All right, we've covered the stationary part. Let's move to the very heart of the machine. Now we're talking about the rotor. This is the part that spins. If the stator is the house, then the rotor is the engine inside, the part that's actually doing all the heavy lifting and converting energy from one form to another.
And the rotor isn't just one piece either. It's a whole assembly of crucial components, all working in perfect harmony. You've got the armature core and the armature windings that sit inside it, the really clever commutator, the brushes, and, of course, the shaft that it all spins on.
Hey, does this sound familiar? Just like the stator's poles, the armature core is also laminated. It's built from a stack of thin, insulated steel discs. And for the exact same reason. As this core spins like crazy inside a magnetic field, it would get super hot and waste a ton of energy if it were solid. These laminations stop those wasteful eddy currents right in their tracks.
Tucked into the slots on that core are the armature windings. Now pay attention, because this is where the action is. This is it. These are the copper coils that are either cutting through the magnetic field to generate a voltage, or they're having current push through them to create the force, the torque, that makes the whole rotor spin. It all happens right here. Okay, now for what is, in my opinion, the most ingenious part of the whole machine, the commutator. It looks like a little copper ring that's been sliced into a bunch of insulated segments. Its job is to be a high-speed mechanical switch, and honestly, it is an absolutely brilliant piece of engineering.
So how does this little magic trick work? Well, as the armature coils spin in that magnetic field, they naturally generate an AC voltage, one that flips back and forth. But here's the clever part. The commutator spins with them, and right at the exact moment the voltage is about to reverse direction, it physically flips the connection to the outside world. This is how it mechanically rectifies the AC, straightening it out into the smooth, one-way DC current that gives the machine its name.
So you've got this spinning commutator. How does power get to it or from it? Well, that's where the brushes come in. These are just simple stationary blocks of carbon, and they're pushed by springs, so they're always touching the rotating commutator segments. They are the physical bridge, the connection that lets current flow between the stationary world outside and the spinning heart of the machine.
Okay, so we've got all the parts on the table. But hang on, there's one more layer to this onion. A design choice that totally changes how the machine behaves. It's all about how you actually connect those armature windings together.
There are two main ways to do it: lap winding and wave winding. At a high level, you can just think of it as a trade-off. Do you need a wide, powerful river that can carry a lot of water at once? That's lap winding. It's your high current option. Or do you need a super tall waterfall with a massive drop? That's wave winding, your high voltage choice.
Let's dig into that a little deeper. With a lap winding, the number of parallel paths for the current is always the same as the number of poles in the machine. So more poles means more paths. It's like opening up more lanes on a highway. You can handle a ton of traffic, or in this case, a really high current. But with a wave winding, there are always, and I mean always, just two paths, no matter how many poles you have. This forces the current to go through way more coils one after another in series. It's like climbing a super long, steep staircase. Every step adds to the total height, or in this case, the voltage gets really high. It's why you find lap windings in things like electric vehicles that need lots of current, and wave windings in high-voltage power generators.
So, as we put our virtual DC machine back together, you can start to see how it all fits. Every single part, from that outer steel yoke all the way down to how those tiny inner wires are connected, is precisely engineered to work together. It's a complete and, really, a truly elegant system. And in the end, it all comes back to this beautifully simple idea. You have a stationary part that creates a magnetic field, and you have a rotating part that interacts with that field. From that simple two-part principle, we have built an unbelievable amount of our modern world. Which kind of leaves us with a final thought, right? From the fan that cools you down to the power tools in your garage, this technology is absolutely everywhere. So now that you know what's inside, take a look around you. The real question isn't where are DC machines, but maybe where aren't they? Thanks for diving in with me on this one.